Let's try this again. All right. So, but we learned the rules, and the rules are very technical, and hopefully over time you're going to kind of internalize the rules. You should not have to prove that something is Boyce code or third normal form. You should kind of feel it, right? Just doesn't feel right, right? You should have the Spider-Man tingle that there's something going on that's not right, right? So ultimately, as we are designing, you are going to see more and more of issues, and you basically, in the back of your mind, are always going to be thinking when you're designing that your relations are in Boyce code normal form. And Boyce code normal form is actually really the easiest, most boring one you can do, because it just says that every single thing in your relation should be implied by the key, right? That's what it is really saying. We are saying it in various technical ways, but really everything should be implied by the key. Let's just try to see what happens when that is not, which we actually did many, many times, but I will go through the example and then kind of show you how that works. So let's say I have this very simple relation. A implies B, B implies C. The key for this relation is A. It is not in Boyce code normal form because of B implies C, right? So this violates it because it's not a super key. So what we can also see with the same example that I had, let's say that I have an instance. So I have A1, B1, C1. Right? And then I have, let's say, A3, which also happens to have, let's say, C5. A4 happens to have B2. So if A4 has associated B, B2, then what should the C be? If I have B2, then I should have C4. Okay? If A5 has B1, then I should also have C1, right? If I also have A5 again, then obviously I also have to have B1 and C1, but by relational data model, this is actually redundant information. So that's not going to be repeated. But the information about B and C is repeated. Actually, I have the same information here 2 times, and the same information here 2 times. And we said that this is not good because I keep repeating the same information, and as a result, if I decided that in fact B1 should be C5, now I have to change it in 2 places. If I don't, it will be a problem. And I cannot state anything about B and C unless I know an A that has to go with them, which is kind of an unnecessary dependency. So, well, instead of doing it like this, we would like to decompose. We would like to say that in one relation I should store A and B, and one relation I should store B and C. So here I can store things like B1, C1, B2, C4, B3, C5, right? And here I don't have to repeat the information, I can only store it once. And here I store all A and B information. Okay. And this relation doesn't have these problems because I don't repeat information about B and C, right? Information about C is not repeated. I can state things about B and C without having any A's. And the A relation basically only stores the relevant information. This is the case because in this decomposed relation A and B, the functional dependency that holds for A and B is A implies B. For this relation, let's call this R1. For this relation, B and C, the functional dependency that holds for R2 is B implies C. So the key for R2 is B. So this is a super key. So this is in BCNF. This is a super key. So this is in BCNF. So both relations are in BCNF, and this is a better model for all the reasons we keep talking about. So basically the idea is that if you went through this exercise and found that something is not in Boyce code normal form, you can convert it by doing that. But when you're doing that, there's a system to doing it. If you just do it randomly, you may cause problems. So that's the thing that we were trying to figure out. So are we okay with this example? All right, so yes. So A implies B. So if you have the same A value, you should have the same B value, right? But not vice versa. There's nothing that says that if you have the same B value, you should have the same A value, right? So remember that the dependency goes only in one. Sometimes you would have both ways, right? So like, that was the example for, that was on Piazza. It could be that social security number implies RIN, and RIN implies social security, right? But that's not always the case. Like student ID implies name, right? Given a student ID, there's a single name. But are all the students named differently? Is it possible for two people to have the same name? So because of that, name does not imply ID, right? Okay. So the algorithm for BCNF decomposition is fairly simple. So if you have, and I'm going to go through with an example. So let's say you have A implies BC, C implies D, and D implies E. So you look at first the relation and find the key. And what is the key? In this case, A. Then mark all functional dependencies that violate Boyce code normal form, both of these. So I need to decompose somehow to get rid of these functional dependencies. The idea is that you have these secondary pieces of information that's going to cause that duplication that I just showed you. So I want to remove that, but in BCNF decomposition, you have to do it one step at a time. So you have the full relation, you decompose, you take one out, see what happens, and then check again. So we are going to do it one at a time. So when I say decompose, you're going to take one functional dependency that violates Boyce code, take it out. So what does that mean? So let's say I'm going to take this one out. So when I take that out, I actually create a relation, let's call this R1, that has only the attributes that are in that functional dependencies. In this case, the any. Okay? Then I'm going to have a relation, the remaining relation is going to be all the attributes in R except for what is implied by this functional dependency. So what is on the right-hand side? In this case, this is E. So this will be what is remaining. So don't remove D and E together, it just remove what is implied, right? This is exactly what I did in this example, where I took out B implies C, then I just removed C from here, because that was the thing that was actually causing problems. So now you're going to use the algorithm that I gave you, basically find what functional dependencies hold for both of them that are implied by the ones that I first gave, right? Project the original set to these two. So this we know is D implies E because that's what I started with. Then this has A implies BC and C implies D. Okay. Find all that implies and then just find the minimal bases. Just find the minimal and then you can do the combination so that you basically put together like A implies BC. I want to put all the things that are implied by A in a single one because that will give me a better relation, but we'll talk about that in a second. Okay? So now ask the same question. So I have two relations. What is the key for R1? D. So the key is D. Is R1 in BCNF? Yes. So almost always you will find this one is going to be in BCNF. This is the one that's more interesting. So what is the key for R2? A. Is it in BCNF? No, because C implies D is still violating BCNF. So I'm going to apply the same algorithm to this one. So that means I have to take out C implies D. So R21, this is going to be C implies D. And then R22 is going to be what attributes? A, B, and C. Everything except for D. I'm going to do the same thing, find what functional dependencies hold, like C implies D and A implies BC. So is R21 in Boyce code normal form? Yes. R22 is in Boyce code normal form? Yes. Okay. So instead of storing R, you should actually store these three relations. These are the functional dependencies that are going to hold for them. These are the keys that they have. And if you follow the rule exactly, all these decompositions are guaranteed to be lossless. Okay. Now you can check, is it functional dependency preserving? To do that, you take all of the functional dependencies that are still preserved, put in a relation. So I have D implies E, C implies D, A implies BC. Is this equal to the original set? This was my original set, right? Are they the same? Yeah. So this is great. This basically fulfills everything that I'm looking for in a decomposition. Okay? It is in Boyce code normal form. Everybody is in Boyce code normal form. It is lossless because of the way that I have done it. You can actually apply the algorithm to this, the chase algorithm, to convince yourself. And it is dependency preserving. Okay? Now, the interesting thing is that when I started this, I had a choice, right? I can choose C implies D or D implies C, right? So you could have chosen C implies D as well, and there's nothing that tells you one is better than the other, except for your, spider sense, okay? You basically have to kind of get the sense that, which one is better than the other. So just to show you what happens when you choose a different one, I'm going to do the same thing. But now I'm going to actually start with C implies D. This is exactly the same thing I did at the end of last lecture, but I did so fast that I don't know if you actually noticed this. All right, let's try the same thing. Okay. And this time I'm going to start with C implies D. So I'm going to write the solution that I found here, just so that you can see. So solution 1, basically I had ABC, CD, and DE. So I had 3 relations. One was CDE, one was CD, and the other one was ABC. Okay. So now let's do the same thing using C implies D first. So I'm going to take this one out first. So I'm going to get R1 CD, so C implies D. The key is C, so this is in Boyce code normal form. What is R2? AB. Yes, AB. Do I have C? C. I don't have D, but I have E, right? Because I took out C, D. What are the functional dependencies for this one? So I still have A implies BC. C implies D I cannot have because there is no longer a D. But I have C implies E, right? So C implies E is implied by the above, and only contains the functional dependencies in R2. What is the key for R2? Still A, still not in Boyce code normal form, so I'm going to decompose this further. So I'm going to do the same. So this one is good. So I have R21 CE and R22 A, B, and C. So this is C implies E. This is A implies BC, right? So both of them are in Boyce code. So this is what I get. Is this the same one as before? So my new solution, solution 2, is ABC, CD, and CE, right? They are not the same. This is still guaranteed to be lossless because of the way that we are doing this, okay? I don't have time to prove, but take any of these decompositions and apply Chase algorithm. So let's look and see, how about the decomposition? So is it dependency preserving? So what I have end up with is A implies BC, C implies E, and C implies D. Is this decomposition dependency preserving? No. What is it lost? D implies E is no longer there, right? So this decomposition is not dependency preserving. So what did I lose? D implies E is not implied by right? So if I'm given the choice between solution 1 and solution 2, which one should I pick? Solution 1 is better, right? Because it actually preserves all dependencies plus satisfying everything else. How do you know which one is better? Well, you kind of get a sense because you had this, long chain. It's meaningful to start at the end of the chain and then go backwards. But it's actually a good exercise to do what happens when you do it in the middle so that you know you're doing it right? So that you kind of can see, if I actually missed C implies E above, I would have made a mistake. So that's why I generally force you to do the wrong one so that you understand that you're actually following the rules. But the sad thing about BCNF decomposition is that there may be no decomposition that preserves all functional dependencies. So there are cases where if you have functional dependencies that has a cycle in them, there is no decomposition that satisfies all of these rules, right? So it is possible that no such solution exists and that it's not really automatic, right? You try multiple ones and then you pick which one is the best one for you. So to be able to solve this problem, I'm going to have a new algorithm. This algorithm you're going to love because it's super easy. It doesn't really require any, you don't even have to turn your brain on for this one. So third normal form decomposition. We are going to now start from the bottom up. In the other one, you decompose one, look at what is left. In this one, we are going to construct our relations one by one. So basically, suppose you have set of f, but f has to be, in both cases, a minimal basis, right? So f should be minimal. This is true for BCNF too. Okay. Basically, it's very simple. Take every functional dependency like this, create a new relation. It's that simple, okay? But there are a couple of caveats, okay? Once you're done with that, you do a little bit of accounting. So, you know, so the caveat one is that you want to remove, if there's one relation that has all the attributes in the other one, then you want to remove the unnecessary ones, right? So remove R2 if R1 has all attributes in R2, right? So if there's another one that has everything, then remove that. I will show you why that happens in a second. The second rule is more important. If no relation has all attributes of the key, of one of the keys, create a new relation containing all attributes of one key. Okay? Those look very easy, right? All right, so let's see. As promised, no reasoning required for this one. So let's try and see. So let's say I have the same one. Right? So the key in this case is A. This will tell me create one ABC, create one C and D, create one D and E. Okay. This has A implies BC, C implies D, and D implies E. Okay. Makes you wonder why we had to do the whole other one, right? Okay. So is there a relation that has all the attributes of the key? Sure. Key is the A, there's a relation that has A in it, and I'm done. So the nice thing in third normal form is that these are all guaranteed to be in third normal form, but you know, it is likely that they are also in Boyce code normal form. So you can actually run this and then see if it is in third normal form or not. So generally you want to use the Boyce code normal form decomposition if there's only one functional dependency that's wrong, right? You just take that out. If you basically are just like in deep trouble, then you start from bottom up, do all your relations, and then do the fine tuning with Boyce code, right? So Boyce code is not like a great thing to do when you have many, many problems. So, did everybody write this one? Super easy. All right, let's try to come up with a slightly more interesting one. So let's try to do this one. All right, I'm coming up with it. Actually, give me one more. I am making a decision. AC implies B. All right, there we go. I have finally made my choices. Tell me what the keys are. Yes. ACNF is one key. ABFNS is the other key. Okay. Is it in Boyce code normal form? No, not so much. And it's not in third normal form either because this is not a super key and this is not a prime attribute. Okay. So we apply the method. Okay. So if I apply the method, I will get one which is A, B, C, and D. So because AB implies CD, I will get another one, A, B, and C, because AC implies B. I will get another one, R3, D implies E. Okay. So I have one for each functional dependency. If I do this, what has happened? I lost F, right? Because nothing implied F, and so basically F is lost. This is the last rule, because the last rule says that is there any relation that has ACNF? No. Is there a relation that has ABNF? No. So then I need to really create one for one of those. So I'm going to create, it doesn't matter which one, but any one of them is fine. I'm going to create ABNF. Okay. What functional dependency holds for this one? Does anything imply F? No. A doesn't imply B, there is nothing. So what is the key for R4? All three attributes, right? Now, one thing you notice between R1 and R2 is that this is A, B, C, D, and this is A, B, and C. So there is no reason for me to store these separately, right? That's the second caveat, that basically if one is a subset of the other, then get rid of that one. Okay. So I'm going to just add AC implies B here, right? I don't need to store that separately. So now you can check. Is R4 in third normal form? Sure. Is it in Boyce code normal form? Sure, because there's no functional dependency that violates. This is in Boyce code normal form as well. So this is in third normal form and BCNF. Third normal form and BCNF. How about R1? What is the key for R1? So AB is a key. Is AC a key? Yes? Right? So is it in Boyce code normal form? Yes. I was trying to come up with one where it would not be, but turns out that this works both. Okay? So I'm going to choose AB, but either one will work. Okay?
Can you name the subset when you break it out? It would be A, B, C, and then the one above would be A, B, C, D.
Right. So ABC is a subset of ABCD. I got rid of the smaller one. Well, right. So basically, AC implies B was actually in both of them, right? Since I already have the upper relation, I don't need to store the lower relation. So in this kind of case, where you may find this is actually not in Boyce code, but in this case it is, yes. No, there is no reason, right? I mean, in real life, that could be. Like, for example, F could be, so it could be that B that you know is never going to have empty values, whereas C may have empty values, you know, but in this case, that's totally random. Questions? satisfies F. F has to be in all P's, right? So basically, there's no way to get F with other things, right? But then given F, you look at what you can add, right? So there is no like a single algorithm that will work, but generally what I do is I pick one of these and then see how far I get, right? Given F and AB, look at how far you get and then see what you can add to it, right? Questions? Yes.
And then the bottom one, the ADF, I got that it
It has no functional dependencies.
so then it's automatically into normal
And BCNF, nothing to violate. Right. So let's talk about some of the mechanics, like things that may be lingering in the back of your mind. What would have happened? Let's say I have CS1, good old days. All right. So let's say I had right, and then you can ask, well, why is it that I want to, put them all together? That instead of this, I am treating this as okay. So do I have to do it this way, but not that way, right? If I didn't do that, what I would get is I would get R1 is AB, R2 is AC, R3 is CD. If I do this one, I get R1 is A, B, and C, and R2 is C and D, okay? There it is here. So both of them are valid ways to do this. Is one better than the other? Exactly. So one of the things is that, it's not like there are rules that you have to do it this way. In fact, this one can be good because, let's say I store A and B in one place and A and C in another place. It may turn out that I store A and C in, one server and A and B in another server. So the good thing is that if nobody is ever interested in C, then I don't need to really waste my disk space trying to store that, right? So in fact, Amazon, the marketplace, they've spent a long time implementing what they call a key store, where basically given the key, you get one attribute, and each of the attributes are stored in different places so you can quickly get it. So for certain applications, that may be perfectly fine. But if it is the case that you always ask B and C together with A, then the other one is the better one, right? So it's not like one solution is better, but as we do more and more of this, we will talk about, those trade-offs. So, it's like, don't take these as this is how you're supposed to do it, but, that's what the functional dependencies are telling you, but both solutions are just fine, okay? So this one allows you to store things in different servers, process queries in parallel, but this one allows you not to get everything you need in a single one. So it all depends on what the queries are. So they are both fine. It's not like you have to do it. You just, we basically right now do it a little bit more formulaic and do it always on the right-hand side, but there's nothing that says it has to be the other way. Okay? So, any questions yet? No? Okay, then let's go further. Okay, let's not stop at Boy's Code normal form, right? So basically, we keep learning things that are more and more restrictive. So you had the first normal form was the simplest thing. It said that no attributes should have set values or complex structure, right? So this is not the right way to do it. So then, of the things that are in first normal form, we basically have a subset of things that are more restrictive. What is the next restrictive thing? is things that are in third normal form, right? Everything in first normal form is, everything is in third normal form is in first normal form, but not vice versa. And something that is even more restrictive is Boyce Codd normal form. Sometimes this is not possible, so this is our consolation prize, that's fine. But it may turn out that things that are in Boyce Codd normal form are still not fully desirable. Okay? That is when we think about something called fourth normal form. You say what? So let's see if I can find my timely example on this. There we go. So let's say I have this relation where I'm storing name of a hero, weapons used by the hero, and the hobbies. And good news, Firefox is available for download. So I have hero, weapon used, and what was the other one? Hobby? All right, hobby. All right. The point is that because of first normal form, I cannot just have a list of weapons and a list of hobbies. So I basically have to write them one at a time. So I have to write things like, move back to this. Husband is playing Tomb Raider. So we talk about Ice Axe and relic collecting. And compound bow and motorcycling. Okay? So my question to you is, what are the functional dependencies for this relation? Does hero imply weapons used? Can you have the same hero for two different weapons? Yes. Does hero imply hobby? Because for the same hero, I can have multiple hobbies, right? More importantly, does the weapon used imply hobby? Given a weapon, there is a hobby associated with that? No. Okay? So there are no functional dependencies for this one, right? So this is actually in Boyce Codd normal form. You with me so far? So if I were to store this, I would have hero, I'm going to give a little bit more space here, hero, weapon used, and hobby. Okay, and my key for this relation will be all three attributes, right? So this is indeed in Boyce Codd normal form, right? But you go back and ask yourself, does your spider sense say something is wrong with this one? So the thing that we are trying to do is to make things kind of modular. But the issue is that is relic collecting has to do with Ice Axe? No. So should I then, because according to this, somehow they are related, right? But indeed, if I have these true, right? So that this is a hobby, then I should really have another thing like for compound bow, relic collecting. Right? If I want to say, because since they are not necessarily coupled with each other, there is no reason that I should store it with respect to that one weapon, but I should store it for every weapon that it has. Indeed, in the same way, since I have motorcycling as a hobby, then that should be for all the different weapons. I should be able to say it. Okay. So the default feeling when you see this is, why would anybody store it like this? Yes. Yeah. Yes, Isaacs, thank you. Okay. So you will tell me, I will never do that. I will basically store one at a time, and then I will document, that that's what the way it's supposed to be, right? So now what you're doing is you are hacking, okay? You are basically creating this complicated data model so that the next developer that comes after you will curse you to the end of time, right? Because yes, I have to remember that it is like that, but it should be like this, right? So you're creating unnecessary complication in your data model that doesn't need to be there. Basically, there is no reason that these two should be actually in the same data model, right? So in the pure sense, you should really store it for all possible combinations because they are not related to each other. But in practice, you should really not store them together. So the idea is that this is what happens when you have attributes that take multiple values, but the values they take are not related to each other. There is actually a formalism for saying that, bless you. It's called a multi-valued dependency. Okay. And it is written something like this. Okay. Now you would be happy to know that there is a whole theory, as much as we have learned about multi-valued dependencies, their closure, simplification, and so on. So we are not going to do all of that, but we will talk about what that means. What that means is that hero and weapon used together is independent of other relations, other attributes in the relation, right? So it is not that one implies the other, it just says that the other attributes are independent of these. Okay? So if this is true, it is also the case of the complement is true. And the complement is something like this. That in this case, hero multi-determines other attributes other than hero and weapon used, in this case, hobby. Okay? So this is considered the complement of the other. It just says that these two are unrelated, but they are, of course, related to hobby. Okay? So the idea is that this is not a statement of implication, it is a statement of independence between these two. Okay? So hero and weapon used is independent of hero and hobby. Right? So they take their multiple values, but the values have nothing to do with each other. And there are actually rules. So any functional dependency can be promoted to a multi-valued dependency. Transitivity holds, but split rule and combination rule do not hold, right? You cannot combine these two because that would be a very different thing. So the idea is that given this, right, this relation is in fourth normal form if your key includes everything in one functional dependency, right? But hero and hobby is not a key. Hero, hobby, and multi-valued is a key. So in this case, I will do a decomposition exactly like voice code. That I will take one of these two out. If I were to take this out, the 4NF decomposition is exactly like BCNF. So if I were to take this out, I will get hero and hobby, and hero and weapon used. And this is like this is like this. It just says that given that these actually take multiple values, it is much better that they are actually stored separately. Okay? So, with all of that, let us just do this exercise from the from Monday. I have some extras if you still need them. And I just want to make sure that at least we do a third normal form. Okay? So if you are more curious, there's some extras here. Okay? And sadly, there is no time for the quiz, so I will give you the quiz to play with yourself, to play with it yourself. Um, I am adding some things here. So I'm going to put this here in parentheses. You should think about what happens if you were to have that. Okay? I'm not going to do the multi-values, but think about what happens. All right, so we're going to do the third normal form decomposition. Now it's actually quite easy. So I'm going to have show ID, show name, show ended. I'm going to have show ID, show number, TV network. Then I will have one with this one, so I will have show ID, season number, These are all different relations. I'm just not giving them any names. So let's see, I did this one, this one, this one, this one. So I'm doing this one now, show ID. So this one says actor URL implies episode cast actor ID and actor name, but it's the same relation as this one. So I'm not going to create a new one for this because this one has all the attributes in it, right? So these two creates the same relation. Okay. Am I done? Third normal form? What's missing? There is no relation that has all the key attributes, right? So in fact, if I actually had the show nickname as an attribute with no functional dependency, so don't treat the multi-valued dependency as a functional dependency, right? It's separate. So it's not a real functional dependency, right? And if I did have show nickname, that means my keys should also have show nickname. Okay. That means I need to create a relation for one of these. So something like show ID, episode number, season number, I'm going to use this one because it's shorter. Actor URL, character name, and show nickname. So if you did the same thing, so you will find that this one's key is show ID, this one key is show number, this one key is the first three, this one key is episode cast ID or actor URL. This one is the first four. And this one is, in fact, all of them. So all these relations are guaranteed to be in third normal form. This is dependency preserving. And in fact, in this case, they are all on voice code normal form as well, except for this relation, right? This relation actually has the same problem that we just had, that you had character names and nicknames, right? But the nicknames that the show has nothing to do with the character names. So this is actually, it's in third normal form, but it's not in fourth normal form. So because I have show ID, don't worry that I will not ask you something this complex in an exam, but I want you to see the process, okay? Given that show ID, show nickname, okay? Then this is not in fourth normal form, right? So technically, I should take this, not in 4NF, and decompose into two. So one is going to be show ID and show nickname. Like this. And the other one should be everything but that. Okay? So this is now in fourth normal form as well. So if I had this kind of thing, that you can still apply third normal form, do not treat the multi-valued dependencies as regular dependencies. And after you have enough of these relations, then look and see if you want to put them in voice code or fourth normal form, right? So generally speaking, all your relations, let all your relations be in fourth normal form, okay? That's actually very important. But doing normalization like this is really crazy complex, right? So we really don't want to actually go through all this effort. So what we are going to do next is to come up with a way so that we don't deal with something this complex to actually figure out if we have a good data model, right? So that's what we are going to do next. So let's give like a nice 5-minute break, and then we'll continue from here. And I will leave you to do the one in the back, so it's going to be simpler than this one.